Hello everyone. Today, I'll be presenting our work on OccluGaussian, a novel method for large-scale scene reconstruction and rendering that addresses the challenges of occlusions and resource constraints. Large-scale scene reconstruction often relies on divide-and-conquer strategies to manage resource limitations. By splitting the scene into several smaller and more manageable regions, each region is reconstructed independently and finally merged to a complete model. However, existing scene division strategies based on camera positions or point clouds. These approaches are suitable for occlusion-free scenes like aerial imagery or open spaces. They overlook scene layouts and occlusions, which are commonly present in indoor environments. Occlusion-agnostic division splits scenes into mutually occluded regions. Comparing two areas in the yellow highlighted region, cameras for Area 1 occupy a certain amount of training time and resources, but contribute little to the reconstruction of the Area 2. In other words, putting them together involves too many training cameras whose average contribution to the region's reconstruction is thus significantly reduced. Our motivation is to build a occlusion-aware scene division strategy that considers scene layout and occlusions. We enhances training efficiency and resource allocation by focusing on cameras that substantially contribute to the reconstruction of specific areas, rather than diluting efforts across less relevant regions, thus finally improving the reconstruction quality. Our technical contributions are summarized as follows. 1. We propose an occlusion-aware scene division strategy that considers the scene layout and camera co-visibilities. The resulting regions barely contain occlusions, and the corresponding training cameras have a higher average contribution, leading to improved reconstruction results. 2. We present a region-based rendering technique that accelerates 3D Gaussian splatting in large scenes. It eliminates much of the time-consuming processing of invisible 3D Gaussians, boosting rendering speeds without noticeable quality degradation. To achieve this, we construct an occlusion-aware attributed scene graph. Node, represent camera, each equipped with coordinate features. Edge, represent mutual visibility between cameras, weighted by the number of feature point matches between their images. This graph combines spatial and visual information, allowing us to distinguish 1. Cameras that look similar visually but are far apart spatially. 2. Cameras that are close in space but have distinct visual appearances. By leveraging both types of information, we ensure that the graph accurately captures the relationships between cameras, even in complex scenes with occlusions. Next, we perform scene graph clustering. First, start with an initial clustering number and use graph convolution-based clustering. Second, refine clusters by splitting overly large clusters, ignoring too small clusters and merging overlapping ones. Finally, calculate boundaries using linear classification models to define decision functions. For each region, we carefully select training cameras, base camera, located within the region. Extended camera, outside the region but providing sufficient visual information. Border camera, cameras facing the region but occluded. These cameras help constrain Gaussian primitives near the boundaries for the final seamless merging. Without the border set, these Gaussian primitives can become very large or elongated, resulting in floaters or artifacts. Finally, we optimize 3D Gaussians for each region individually using its selected training cameras. After optimizing 3D Gaussians per region, we remove primitives outside the region to create sharp borders, enabling seamless merging of regions into a complete model. Rendering large scenes with millions of 3D Gaussians is computationally expensive. Our solution is, first, we pre-cull invisible primitives using occlusion and visibility checks. Second, we subdivide regions to reduce interference from neighboring regions. Finally, rendering with region-based culling, identify the viewpoint's region, cull invisible Gaussians, and render only what's necessary. This approach reduces rendering load while maintaining high visual quality. We present quantitative results for occluded scene reconstruction. OccluGaussian almost significantly outperforms the compared methods in all metrics, especially in PSNR. Our method maintains a clear advantage, highlighting the generality of our approach. These results shows the effectiveness of our scene division strategy, which enhances the correlation among training cameras within each region and improves reconstruction quality. Thank you for your attention. For more details, please visit our project page.